have homework 3 releasing this weekend as well, for homework 3 part 1 and homework 3 part 2. And now I'll just get started with the Recitation 7. I know Biksha hasn't gone over CTC directly yet in lecture. He'll be going over it later, so I'm gonna go over it in like a high level, like more a different perspective, and he'll talk more about the training and more about computing divergence about CTC decoding. So yeah, that's that. Can everyone see my screen? That's right. Yeah.
Yes.
So sequence modeling. So our problem usually is a length n vector from x1 to xn usually, and we have an output sequence from y1 to ym. So like in homework 1 part 2, you originally had a sequence that usually took in like Mel spectrograms and outputted like the phonemes for it, phoneme recognition for it pretty much. And the sequence usually was ordered. The input and output were in the same order that they were respective to. It doesn't have to always be ordered. It could be in different orders. For example, like if I'm converting from one language to another language, the sequence, it goes out in different orders. And that's more, we don't really go over a model for that right now. So I'll go over something where it's ordered actually. So on the left, we have a sequence of inputs that produce a single output. And that was more basically the homework 1 part 2. And homework 3 part 2, we're solving a different type of problem. So it's the right model kind of. So how do we do the following? Like how do we train such a network to do the following? Like what do we output currently? So basically the previous model over here is just a concatenation of all these smaller models over here, smaller models right here. So we basically want to model that given a sequence of inputs, we output a sequence of symbols pretty much asynchronously. And this is what you'll be doing in homework 3 part 2. Giving an input of that Mel spectrograms and be outputting at given time steps the correct phoneme. So we'll assume that the model in the previous or in the intermediate steps will be also outputting those phonemes too. So you could assume here, here, here. So that means you could assume that that same B comes out here, IY comes out here, F comes out here, and so forth. So each network outputs a probability distribution for each for the output symbols and at all times. How do we find like the most likely symbols though for each at these time steps? That's another problem we have to deal with. So I'll not be discussing how we compute the divergence for such a sequence after we get the outputs. So I'll be discussing how we just go about training it, I guess. And I mean like when I go about training, I mean like how we output these symbols in this manner. So the first solution we can go about is we select the most probable symbol or label at each time step. So we have a probability distribution here, continuously throughout all these symbols. We'll select the most probable one at each time step, so forth. There's one issue with that. This isn't the most probable sequence of symbols. And at Big Show, we'll go over an algorithm called the Viterbi algorithm to discuss why isn't that the case. The second issue, which we will discuss, and we'll discuss a solution for that, is that we cannot distinguish between an extended symbol and a repetition of symbols. Because what if I had another B here, and that was part of the solution, but I would have had BB, I would have got rid of it. So we need to distinguish between those symbols. Another solution we can do about it is impose external constraints on what sequences are allowed. So we don't know, later on we'll see, we don't know how we know we got a B here, I, Y, F, and I, Y here as well. So this is not most likely the most ordered synchronous output. It might be a time synchronous output sequence, and this will be more discussed in lecture as well. So this is the issue we're talking about in the previous slides. When do we output these specific symbols, and in what order, at what times? Are we putting at the correct order and correct time step? So we're going to model our network on the right, like how it is so far, and we're going to output, take the max of at each time step to make sure which label we have. So basically we have to apply both solutions because we're having these multiple issues we have here. So to deal with these issues, at each time step in the network, we output a probability for each symbol, but we will only block out all the rows that do not include the symbols from the target sequence. So B, IY, F, and IY. So we'll block out those rows because since we're training the algorithm, we already know what the target sequence is gonna be. So we can block out AH, D, EH, F, and G. Because we know the most probable, now we need to know when we output it in this network. So now we can compose a graph. So every path from the source to the sink. So when I mean the source to the sink, this is the source of where we start. This is the sink because we know the order has to go from here to here. We know it'll never, we know that we'll have a node where it has to start. B has to start here, and IY has to end at this last thing. So we can create a graph from this probability distribution, pretty much. And the graph will look like the following. And the probability at the edge will have to be 1 here at y0 to B and y8 IY at this time step. And then we know the probabilities at every other corresponding spot because we outputted this distribution in the previous step. No matter what you do, before you even do this step of constraining the network to these symbols only, you first output a probability distribution at all the time steps. After you get a probability distribution at all the time steps, then you constrain the graph, constrain the output or graph, and then compose the graph. That's what we do here. We're having the same issue as before in the issue slide where we cannot distinguish between an extended symbol and a repetition symbol. So we're gonna have to deal with that as well. And then Big Show will discuss how to find the most probable sequence in this graph using the Viterbi algorithm, using the forwards and backward algorithm, pretty much, and how do we compute the divergence after we've got the most probable sequence. So we still have the repetition issue. So if I output the following sequence here, do we know it's rod or root? And then we have to introduce another explicit symbol which serves to separate from these other versions of these symbols. And this extra symbol right here will be a blank symbol. That we'll need it to be trained over too. So our final graph will look like the following. We'll have these blank symbols over here, and we're only gonna train over. We're only gonna have 5 of the things. So we'll compose the graph with the blank everywhere. The reason we're doing that is that so we know that whether we can have multiple repetitions or we can have multiple interleaved symbols. So like the following here. So I have a blank here, here, here. And that makes me know I have the O here. But here I have the blank here, and I have RR, then ODD. So, but we only need to have a probability distribution for one blank. You're not training over multiple blanks. It's just one blank. Then we just compose the graph like this. So the overall training procedure for connectionist temporal classification, basically, that's what we were basically doing this whole time, is setting up the network, which will be composing many LSTMs, and initialize the network with the blank symbol. Then we'll pass these training instances through the network to obtain the probabilities for all the labels and all the symbols. This is really important. Make sure it's everything. We're composing for everything. Then we'll construct the graph on this previous page, the same graph. You have to make sure to include the blank symbol as well when you're outputting the probabilities. And then we'll apply the forward and backward algorithm, right, which we'll go over lecture to find the most probable sequence. And then we'll compute the divergence for the most probable sequence we have obtained. And then we'll update the parameters in the network. And this is only regarding the training. So if I'm testing, I don't know what the target sequence is. So we're gonna have to deal with that as well. First, I'm gonna go over how we deal with NN-CTC loss in the Jupyter notebook. And then Tony will discuss beam search, which is more about how do we test this. That's for testing. This is only for really training. So can anyone see my Jupyter notebook? Okay, any questions? Anyone questions? check the chat. So we're basically given a data set, the toy task data set, and this isn't the greatest data set for this problem, but it's more about going over an example. So I have my data here, I have the letters in my data set, and I have the respective phonemes for that data set, the outputs. So I'll input my necessary libraries, and now I'll make the X, the data actually, which is just find the letters for every word in here, pretty much, and make it a tensor. And then for the labels, I do the corresponding, find the correct pronunciation of that word in the phonemes thing. So find the correct index. And then I have to also save the lengths, and this is pretty important. I don't think you guys went over this so far in homework 1 or homework 1 part 2 or homework 2 part 2, but in homework 3 part 2, you'll have things where you'll be dealing with variable length of sequences. So you have to be able to deal with that. So you must record the length of all the things in X and all the things in Y, their output sequences, because they'll be different. Oh yeah, okay, I'll go back to the blanks quickly because we do have time, and that's something that is confusing. On lecture, we will go over that again. The whole reason behind the blanks is the same issue I discussed here, where we cannot distinguish between an extended symbol and repetitions of symbols. So what I mean by that is that if I had a B here, since I'm gonna condense the whole network just to be B instead of B. I'm losing that information. So I'm always gonna have one symbol only. But what if I actually did have a B here? And I'm not just condensing the network. But to be able to deal with that, so when I compose the graph like here, it has to have a blank in every spot so that it's possible that if I have a B here, I can output a B here, right? Then there'll be a blank, and there'll be a B here, then a blank. So I know I have two B's. But if I did B, B, it'll just be like one singular B. So if I had R, it would just be one singular R. Versus if I had B. Okay.
Sorry. Sorry.
Yeah,
Can
go
I
ahead.
when do you want to like say condense the RR into one R, and then why do you want to like take the I think Tony said like the word beef and then separate the two E's. I got a bit confused at when you want to like separate those and then when you want to like condense those.
So if in my network, say my target sequence is um uh uh rod, like that. Actually no, say it's this one, the below one, rude or whatever, rude, or this one, the second one right here. How would you distinguish between these two? Like if you looked at these two symbols sequences, um basically the way my network condenses, it gets rid of repetition. So ones that are adjacent to each other, it makes it into one singular label. Do you understand why we do that? Like why would I condense this into one R?
I only like need to detect one R.
Yeah, correct. What if I
Okay.
wanted to detect two R's? I would have to include an explicit blank between them because this is very different from this.
I see. Okay.
Yeah.
So like
So
this CTC problem is like detecting a certain pattern, like not necessarily the whole word.
yeah, so it's finding the
Okay.
most probable sequence such that it has a blank in there and a blank here, and that's what
Okay.
it found. Yeah.
Cool. That's pretty clear. Thank you.
Okay, so back here, I think we just talked about padding the sequences for X and Y. And so when we pad the sequences, we'll pad them it'll be padded in respect to the longest sequence. And we have to pass batch first into the sequence because that's what it requires for CTC loss. And so this will be the longest sequence. So I think it has to be padded in regards because of this one long sequence that's messing up everything. Actually, these two long sequences. So now we just construct our model. So we have an embedding layer pretty much. We have an LSTM layer and then an output linear layer. And then in our forwards, we basically call the network on our embedding layer. We pack this. So this is a new function we actually, this one right here and this one right here are new sequences. So we have to combine the information for our lengths of our X sequence and X together. So there's a function called pack padded sequence. which takes in, I think this one's it. So it takes in the length of the longest sequence, which was, in this case, was 4, or it takes in all the lengths of the sequences, right? And it takes in B is the batch size, and then, am I interpreting this wrong? So it'll take in the X right here, and it'll take in the length of those sequences. And we don't want it to be sorted because we're training right now. And basically, it'll output a sequence that is a combination of those two. It'll combine into a singular tensor value. And that's what LSTM will be required. And then after that, we'll get an output from the LSTM. And then we'll have to undo what we did before to get the Y lengths. And then we have to compute the log softmax as this is required for CTC loss. Can anybody hear me? Because my connection's not that great. Oh, is everyone following this too?
Yeah, you're coming in and out a little bit, but it seems to be okay still.
Okay. Yeah. Sorry about that. So you do compute the log softmax, and then for NNC, because you guys required for NCTCC loss. Okay. So then this is the documentation of CTC loss. It takes in 4 arguments, the log probabilities, which we just computed in the previous slide on out, on the target values, which are given in Y and Y lengths, and then the input lengths, which were given as well. We had over here, and then we also had the target lengths as well, right here. So we have all those things, and now we have to first construct the model. So we have to construct the model, so we know it takes in 4 things: the in vocab, out vocab, embed size, and hidden size. So we know the length of our letters, length of our phonemes. This is the output, and this is the input based on the number of letters they are. And then this is very arbitrary for now, or yeah. And then we construct our criterion, which is N and CTC loss. Before we didn't usually have this. There was other third-party libraries we had to use with Corp CTC, but this is for now. Then, so let me just run this actually. Hopefully it runs. I was running this morning. Okay. Yeah, and then pretty much we go through each epoch, we zero it, we pass in the X and X lens as this is needed in the model itself for a CTC loss. Actually needed for the LSTM actually itself too. Then we compute the loss based on this thing and put in the correct arguments, and then we get the loss out backwards, and then we step. So if I run this, trains pretty much quickly. And then Tony will go over about beam search and then testing the following sequence. So if I already have a trained network for such a problem, how do I get that correct? How do I test it without knowing what the target sequence is in the case? Any questions, anybody? So Tony, you could start, I guess, right?
Yeah. Okay, so you can see the screen, right?
Yeah.
So, get this. So once we have this output and we're trying to validate or test it, we don't know what it's supposed to be. So before we knew it was supposed to be like beefy, but now we don't know. So how do we find the most probable output? And just in this diagram here, you can see each X0, X1 might be like a Mellon spectrogram. And each of these probabilities is like the probability that this output is AH, for example. So one possibility is that we just do a greedy decode, choose a symbol with the highest probability at each time step. But this might not give great results. How this would work is that you take the highest probability, say it's like B, and then here could be E right here, and so on. Usually that won't give great results. So we want to find the most likely symbol sequence. And one way to do this would be to find all decodings, but this would be exponential in time because you would need to construct, like it'd be like 1, 2, 3, 4, 5, 6, 7, 8. So it'd be like 8 to the T number of possible sequences you'd need to consider. So here we're going to organize the possible symbol sequences as a semi-tree, and I'll show you what that is. Basically, in this semi-tree, each node here represents like a unique output. And in this semi-tree, we have only 3 symbols, the S1, S2, and the blank symbol. And we can see that each symbol connects to every symbol other than itself. See S1 here connects to S2 and the blank, but not S1. The reason being, again, we want each node to represent a unique output. And this symbol repeats itself. And again, the point is that each node represents a unique symbol sequence. So any node on here, let's pick this one. This would represent S2, S1, S2. And in this diagram, we just kind of unrolled this tree to represent it in this form. And these red paths represent the paths that we could take to get to some unique output. You can see there are a lot of paths here. And this alpha just means what's the probability of the sequence at the end. And like we want to select the symbol sequence with the highest alpha. So how do we do that? So again, this graph will get exponentially large. So we can just use a tree search with a beam. So we consider at most k paths at each time. And we prune every time we take a step down the tree. So the inputs we have to this beam search are the beam width. You'll have to find through experimentation what works well. A larger beam width means longer computation time. And also we have the symbol set. So the set of symbols not including the blank, and you'll see why this is. And then we have the array of probabilities, which is just the output of the network. It's going to be a shape, the length of symbols set plus 1 because we don't have a blank in the symbol set, and T, the number of inputs. So I'm going to go through this pseudocode. This is going to be really similar to what you're going to actually have to write for homework 3 part 1. And you can also use this for homework 3 part 2 when you're testing and validating. So, okay, first of all, I'm going to ask a question here. I'm going to pick randomly. Let's see. All right, Yash. So before we could construct a graph like this, represents beef. So why can't we do that now?
Can you repeat?
So yeah, so before we could construct this table here that represents the word beef. And I'm asking, why aren't we doing that now for decoding?
Yes, because we don't know actually time sequence, there'll be like probabilities for all the uh, output.
Okay, I think you're close. The answer is because this is for like training when we know what the output's supposed to be. We know the output's supposed to be beef. But in our case, when we're decoding,
We'll have probabilities with all those phonemes, right? So that's why.
well, actually, to construct this table, we took the Ford input and we just like copied the blanks here, and we copied the E here. We construct this table because we knew that the output's supposed to be beef. We have the label pretty much, but when we're validating and testing, we don't know what the output's supposed to be. All we have is this. We have no idea it's supposed to be like beef or anything. So
Yeah.
we're gonna have to find what the output's supposed to be, just based on following paths and hopefully finding the path with the highest probability.
Okay.
All right, thank you. So going back to this beam search, we'll go through this step by step just to kind of give an overview. We're gonna have these paths with terminal blank and path with terminal symbol. These are gonna be just a set of paths. You can represent them with each path with a string. And one thing you should note is that these paths with terminal blanks, we don't actually put a blank at the end. They're gonna have a normal character at the end. And we know that they have a blank at the end because we store them in this path with a blank at the end. So first we're gonna initialize these paths. So this is just paths with one symbol in them pretty much. You can see it here. The three paths we are gonna have are the blank, S1, and the S2. So this is how we initialize them. It's pretty simple. So we create these two blank path scores and initial path scores. And we also are going to create the paths with blank and paths with final symbol. So we're going to start with the blank one. What we're going to do is we're going to set the score to the corresponding element of the output here. And we're going to set the path equal to, you can see here it's null. So that's how we're going to represent the blank path with just a null. And then for the symbols, for each character in the symbol set, in this case it's S1, S2, we're going to set the score equal to the corresponding probability, and we're going to add that path to the paths with final symbol set. Very simple. You can see the result on the right. And you're gonna run this for loop for the number of inputs here, or the number of outputs. It's going to, number one, it's gonna prune so that you're considering only beam width paths. Number two, you're gonna extend every path with a blank. And number three, you're going to extend every path with a symbol. So we're going to come back to this pruning, but first we're going to see how we're going to extend every path with a blank. You can see in this graph here, the red highlighted ones, those are the, this is what we're doing right here. See, from S2, we're extending with a blank here. And if you already have a blank, it's the same sequence here, or same output. So here's the function extend with blank. We're doing two things here. We're extending paths that already have a blank, and we're extending paths that end in a symbol. So here's how we extend the paths that already have a blank at the end. First, we create an updated blank paths and the corresponding scores. And we're just going to add this path to the paths with terminal blank set. And remember, these paths don't actually have a blank at the end. We know they have a blank at the end because we're representing them in this set. And then we just, the score is the current score multiplied by the new blank score. So like when we're going from here to here, we have to multiply by the probability that it's a blank at time step 2. And then we're going to extend the paths with a terminal symbol. So for every path in the paths with terminal, this is saying for the paths in paths with terminal symbol, if it's already in our updated paths with terminal blank, that can happen because we could have added it back here. We're going to add the probability, and this can happen. For example, take the instance of this one, S2 and S2 blank. We can already have S2 blank here, and when we're adding a blank to S2, we're going to just add the probability. And otherwise, if it's not in the updated paths with terminal blank, we're going to add this path to the set, and we're going to set the probability right here, pretty simply. Oh yeah, this represents setting the paths that end with a blank here with another blank. And this represents extending paths that end with a symbol with another blank. And after we do this extend with blank here, we're going to extend all the paths with a symbol. And you can see the highlighted lines represent that. So we have S2 going to S2, S1, for example. And this is done in a similar way. First, we're going to extend the paths that end with a blank and add a symbol at the end. So you can see we're adding a symbol at the end here, and we're going to create an updated paths with terminal symbols and add this new path to that set and set the probability here. This again represents when we have a blank at the end and we're adding a character at the end of that. So we have S2 blank, and this is going to S2 blank S2, for example. And then we're going to extend the paths that end with a symbol already with another symbol. So one thing to note is if it's the same symbol, if we're trying to add S1 onto like S1, we're not going to do that again because that would represent the same thing. We just collapse into a single S1. So this is saying if the symbol is the same, we just keep the path that we already have. And then again, we're going to, if it's already in a list, we're just going to add the probability, and otherwise we're just going to add the path to the set and set the probability here. And yeah, this represents when we already have a symbol at the end and we're extending with another symbol. And you can see here S2, if we try to extend with another S2, it doesn't do anything. It still represents the same final outcome. All right, any questions? No? Okay. Next, we're gonna go over the pruning. So after extending with a blank and extending with a symbol, we're gonna find that we're gonna have more than beam width paths. So we're gonna need to prune at each time step. So yeah, consider this instant. We might be considering all these paths right here that might be more than our beam width. So we're gonna need to prune some of those. And pruning is very simple. It pretty much has, I'd say, 3 steps. Number one, you it's put all the scores into a list. Number 2, you sort the scores to find the cutoff score. And then number 3, you keep the paths that have score greater than the cutoff score and then discard the rest. So first, you're gonna gather all the relevant scores. It's very simple for all the paths and the paths with terminal blanks and the paths into paths with terminal symbol. You're gonna put their scores into a single list. Yeah, here we're just considering all of these right now, and we're gonna prune some of them. Then we're going to sort the list and find our cutoff. Cutoff is just going to be the kth largest score, where k is our beam width. And next, we're going to keep the paths with a terminal blank if they have a score above the cutoff score. So you can see right here, if they're above the cutoff, we add them to the new paths with terminal blanks. And in this diagram, it shows we're considering the ones in yellow. And it seems like we're keeping this one here and we're discarding the 2 with a black circle. Because they didn't make the cutoff. And in this one, we're similarly, for the paths with terminal symbol, we're doing the same thing. We're considering the paths highlighted in yellow. And let's see, it seems like if it's red, we're keeping it, and if it's blacked out, it didn't meet the cutoff, and we're discarding them. So in this case, we're discarding 5 of these. It seems like we're keeping 1, 2, 3, 4 paths. So that's how we prune. And this is just pointing out, why is this here, not at the end of the loop? Because we don't want to prune the paths at the final time. This loses information. Instead, at the final time, we will merge paths that represent the same symbol sequence. So I'm gonna pick on a random student here. I'm gonna ask them to explain that. Yifan Peng, could you elaborate on that? What do you think that means? Yifan Peng, are you here? No. Okay. I'm gonna pick another. Mitch Fogelson. Can you explain what you think this means?
I was not explicitly paying attention, sorry.
Okay, that's fine. I can explain this. So, see, basically, consider that we prune this blank path here. We prune this blank path, but we're keeping this S1 here. This can be an issue because later on, this blank path would contribute to this S1 because from this blank path, we can go to S1. So every time we prune, these issues can arise. So we just want to mitigate this at the very end by keeping, for example, both this S1 and this, or how should I explain this? Oh, that's a bad example. Okay, consider S1 here and S1 blank. At the very end, we want to keep both of them because they represent the same like outcome. They both represent just S1. So if we prune them and we somehow get rid of the S1 blank, but keep the S1 in this case, we're going to have a less accurate probability for S1 at the very end. That's pretty much it. So at the very end here, once we have our K highest probability paths, we're going to merge them. So again, we could have like S1 and S1 blank, and we're going to merge them because they represent the same final outcome. Yeah, you can see it here. We have S2 blank in blue, and those are going to be merged, and then S1 and S1 blank are going to be merged. So this is pretty simple again. What we're doing is we're going to create a merged paths and a final path score. And for every paths in a terminal blank one, we're going to put it in the merge paths. Blank. Oh, I see. So this is just taking a shortcut. We're setting merge paths to be the paths with terminal symbol here. So this set already contains all the paths in the ones with the terminal symbol. So we just need to do a for loop on the paths in the paths with the terminal blank here. And if it's already in here, we add the probability. Otherwise, we set it here. Let's see. Dhruv Vaishist, can you tell me in what case the path will already be in the merged paths?
I'm sorry, I just joined the lecture. I don't have a very good idea. And
okay.
Yeah.
How about Harry J? Do you have any idea? Harry.J.
Yeah, could you repeat the question?
So in what case will this if loop run? So in what case will this path in the paths with terminal blank already be in merge paths, which is our paths with terminal symbol?
Why don't just the original case with like no paths be like the default essentially?
No paths. Well, let's see. I'll give you an example here. So P could be like, it could represent like S1 blank, this P right here. And the reason it could be in merge paths is because this S1 blank we're actually representing as just an S1 again. In the paths with terminal blanks, we don't actually have a blank at the end.
Right.
So you could have an S1 in the normal paths with terminal symbol, and that's where you would add the probability here. So after you merge the paths, if you're done here, you just pick the path with the best final path score. Okay, so that might have seemed like a lot. This code is actually pretty simple though, and it's going to be very similar. It's going to look very similar to the code you're going to have to write for homework 3 part 1. So this pseudocode you're going to find to be very useful. But yeah, Sean, do you think we should go over the CTC decode?
Yeah, I'll go over it, but it's not working
Okay.
anymore for me. It's just like-
Okay, I mean, just tell them about it maybe.
or do you want to go over it? It's up to you.
I don't have the Jupyter notebook pulled up.
Okay,
right
I'll go
now.
over it. Yeah, that's fine. Just stop sharing. And then,
Sure.
yeah, I'm just gonna restart my notebook once. Second, I want to make sure. I have the saved outputs from last time, so maybe this will help. But yeah, can everyone see my screen?
Yeah, we see it.
Yeah. Okay. So before we stopped at this training loop, pretty much we finished training our model. Now we want to begin testing our model. So there's a library called CTC decode, which finds the most probable sequence from based on the probable distributions you would have got from your training. So after you train the model, you have a complete model, and then say you're testing. So you pass an input, and you'll get an output. Your output will be a probability distribution of the log probabilities that are from this model right here, and you'll get their out and their out lengths pretty much. And basically with CTT code, you'll pass that in, and they'll give you the most probable sequence based on the labels you have provided. So basically these are the commands for doing this. I actually had issues downloading it right now again. I don't know why. It was working this morning. So if you do have issues, you could post your error on Piazza, and we'll try to help you as much as we can. There's no guarantee we can solve it because we're running into the same issue. And there's some, with updated PyTorch, there's people are saying that there's no support for it. Some people are saying there's no support for it, so you might have to downgrade your PyTorch version. So I'd recommend, if it doesn't work, when you implement beam search for homework 3 part 1, which is required, implement it with taking into account batches. So when you implement it homework 3 part 1, there's no requirement for you to take into account batch size. So I recommend you do take into account batch size, as that is pretty important, and it'll be easier for it using it. Even though it's written in Python, it'll be slower than this library because it's written in C++. It'll still be about the same. You could probably just reduce your beam width to at least slightly smaller, and it'll probably be about the same. Like, significant difference in beam width doesn't really actually change your model considerably in terms of accuracy. Like, I remember trying like 100 versus maybe 1,000. There was no significant difference. Actually, there was no difference between 1,000 and 10,000. But you always try greedy search too first before you try beam search. So pretty much after we say we do have this library installed, we import the library, we initialize the class for it, and then this is our probabilities. So say we do have a probability vector out of the vector, and then we get say we're passing in probabilities pretty much here of each of the distribution of the labels, and then we're getting the size of those, predicting that, and then we're passing in the probabilities and the number of labels we have. So we have 2, and then we're printing out the output pretty much of the most probable sequence. And then we're doing the following. We're just gonna do the same thing. We're gonna import numpy here, numpy, and then matplotlib, and then visualize the data pretty much here. It's a visualization function. And this is our test data. So we have the following things. First, we have to do the same things we did before. We have to convert it into letters. Then we have to find the length of each sequence and then pad it. So we have them where the longest sequences, of course, sent these 3, and this one's only 3. So we need to make sure we know the lengths of each sequence. When you pass in CTC beam encoder, you don't need to pass in the actual symbols. You can just pass in, for example, $sign and the number of phonemes we have. So this case, I think we have, I forgot, it was over above. We had about 8 phonemes before, including the blank. We pass in the same number of phonemes here. The beam width, this is up to you. And then you have to pass in log probo as input is true, as we're providing this. We've already talked about this. Then basically we run the model on the test data. We get our output and output lengths, and then we flatten it pretty much, and then we pass in our output lengths, and we pass in the decoder decode, and then we just, after that, we have our output, and then we can just visualize the data pretty much to see the following. Basically, you will run into issues with CTC beam decoder if you don't pass in the correct arguments in the correct thing. It will crash your notebook completely. So make sure you save your model. If you didn't save your model prior to doing this, always run greedy search before, just for so you have a test for your CSV. I recommend, I did both. I think I used beam decoder and I used my own Python beam search. And if you have any questions, let us know, because this is pretty important for homework 3 part 1 and homework 3 part 2. Beam search is important in both parts, and then CTC loss is important for part 2 specifically. Yeah. Anyone have any questions?
And again, you might not need to do this for homework 3 part 2. You could get the A cutoff with just a greedy search.
Yeah,
But that will be much more
easy.
difficult.
Yeah. I think with the small beam width, you're able to do it, right, Tony? Like you don't need to like last semester's, right?
I think with just greedy search, I was like really close to the A cutoff. So yeah, I mean, I think that's it for this recitation. I know many of you might not be done with homework 2 yet, so like good luck on that. And hopefully you can get started on homework 3 soon.
I guess we'll start up the recording now.